Hello everyone, today I'm going to do a presentation on the topic of static. I would like to start by introduce myself. My name is Sujai and my matrix number is 200721. Today's presentation is going to be divided into 4 parts. First, I'm going to talk about the basic concept in static. Second is force system. Third is equilibrium. Last but not least is friction. Alright, let's start by talking about the basic concept in static. There are 4 basic quantities, which are length, time, mass, and force. As we can see, here are the SI unit and here is the FPS unit for length, time, mass, and force. And here is the table for unit conversion from FPS unit to SI unit and also from SI unit to FPS unit. Okay, now I will talk about idealization. Why we need to talk about it and why this is important. This is because idealization is very important for us to simplify the application of theories. There are 3 important idealizations. First is particle, which has mass but size can be neglected. Second is the rigid body, which is the combination of a large number of particles. Last but not least is the concentrated force, which represents the effect of a loading which is assumed at a point on the body. Now we will talk about the Newton's 3 laws of motion. For first law, the particle, this is the particle, original at rest, or it moves in a straight line. With a constant velocity, it tends to be equilibrium, or in other words, it means like it's not subjected to an unbalanced force. And for the second law, the particles is added by a force, which is an unbalanced force F here, and if you experience an acceleration, this is the acceleration has the same direction as the force, which is goes to the right. So these particles will experience an accelerated motion. And here comes the formula for the second law, which is F equals to ma. Then here is the third law. When we have an action in this way, we will have the reaction in the other way, which is equal to the action and also collinear with it. Okay, for further understanding, I would like to talk about a real life example. Yeah, I know this is very cute, but this is a very relatable example to our third law, which is the baby swimming. When the baby push against the water, which is the action, and the water will push back the babies, which is the reaction, will push him forward. So this is the third law. Okay, now we are going to talk about the second part, which is force system. There are 2 categories. First is the scalar, and the second one is the vector. Scalar is just simply a positive or negative number, which are, for example, like mass and temperature. For vector, we have magnitude and direction. For example, like velocity and momentum. As we can see at the picture here, the arrowhead is represent the direction of the vector, and here is just represent the magnitude of the vector. And for the vector operation, we have like multiplication, division, yeah. So when we multiplicate a number, like we multiplicate 2, it will become 2a. Like if it's 0.5, it will become 0.58. If the scalar is negative, the vector will become the opposite direction. Like if we multiplicate negative 1.5, originally it is like this. When we multiplicate with a negative number, it will become the opposite direction, which is like this. So if a vector are collinear, the resultant is just simply you add each of the vector. Like we have a vector A here and vector B here, and so for the resultant we just add A plus B like that. Yeah. So the next one is parallelogram law, which is how to build the parallelogram. Like we have the first one, like this and force 2 like this. So we need to draw 2 lines, which is parallel to force 1 and force 2. After that, we can draw a resultant force which is diagonal, which is diagonally like this. This is for parallelogram law. Like for triangle rule, it is just simply we take it from here. It will become the triangle rule. Or another way is tip to tail method. And this one is our force 2, right? And we move our force 1 into this way, which is tip to tail, tip to tail. Yeah, so and this is the resultant force. Yeah, okay. So now we need the law of cosines and law of sines help us to solve the problem. Here is the formula for law of cosine and here is the formula for law of sine. And for the 2 dimension, we can divide the component into fx and fy, which is the x component and y component. When we have a lot of component, we can just simply solve it into, we can resolve it into x component and y component. We can like sum up the x component, we can sum the f1x, f2x, and f3x become the fx, and after that we can sum the fy, which is the f1y, f2y, and f3y into fy. Yeah, we can just sum it like this. After that, we want to get, this is the resultant force in x component, and this is the resultant force in y component. After that, if we want to get the magnitude of the resultant force, we can use this formula. And we want to get the direction at here, we can use the tangent -1. We use the y component divided by the x component here. Okay, now I will talk about the unit vector. Okay, this is the unit vector. It has a total length of 1. How can we get the unit vector? We just simply use the f. This f is like we have the ijk and divided by the magnitude. So how can we get the magnitude? We can get the magnitude, the magnitude here by using this formula. And now is the coordinate direction angle, which is alpha, beta, and gamma. Alpha is from here to here, which is the resultant force from the x-axis. Beta is from the y-axis, and gamma is from the z-axis. Okay, so to get the coordinate direction angle, we can use this, which is as I as I said just now, which is the unit vector at here. Okay, we can use the x component divided by the magnitude. This is the ijk. So here are the formula, and another formula for it is when we sum up the alpha, beta, gamma, the cos, and we get 1. The unit is equal to 1. Then after that, for the resultant force, we represent it in this kind of form. We have I, J, and K. I is for X, J is for Y, and K is for the Z direction. And we have position and force vector. And for the position vector, if we want to get A to B, we just use the coordinate of B minus the coordinate of A. We use the X minus A, which get the I direction, and J direction, and K direction. And this is for the force vector as well. If you want to get the resultant force, we just use the magnitude times with the unit vector. Okay, now this is the dot product. The dot product, we just use like A times with B, we just use AB cos theta. This is the theta here is the angle of the vector. Okay, then here is also the formula for the dot product. And if we want to get the resultant force at here, we can simply just use this formula. Okay, let's look at the example. Like we have two force added on this hook, which is force 1 and force 2. And we don't know the magnitude of force 2, but the question told us that there is a resultant force, Fr, which acted along positive on the x-axis, which is at here. And we have the resultant force, we have the magnitude of resultant force, which is 800 Newton. Okay, let's see how can we solve this question. As we can know, the resultant force is force 1 add with the force 2. So we need to write the force 1 in the Cartesian form, which has the ijk. So the F1, which is here, we have the 300 cos 45 degree plus 300 cos 60 degrees and plus with the 300 cos 120 degrees. Okay, after that, this is the Cartesian form of force 1. And for force 2, we don't know. So we just write it F2x I plus F2yj and F2zk. And since Fr has a magnitude of 800 Newton and is added in the j direction, so it is positive 800 J Newton. Like we use back the formula we use at here, we write at here, which is Fr equal to F1 plus F2 we use at here. So the Fr is this, we just substitute, and F1 is this one, we substitute at here, and F2 is this one. And after this, which is equal like this, we can just equal it. Like I, we don't have I here, so means this one equal to 0. And J is equal to 800 and K also equal to 0 because we don't have K here. Yeah, this is what I mentioned just now. So we get the F2x is negative 212.1 Newton, F2y is 250 Newton, and F2z is 150 Newton. And we can get the magnitude of F2 by using the formula that I mentioned just now. So we get 700 Newton, and we can determine the angle. Okay, this is the angle we get. So this is the pictures, and we get it just now. So this is the force 2, we get the magnitude is 700 Newton, and force 1 is already mentioned that there is 300 Newton, and for the resultant force is 600, and this is the number we get, and we can put it here. And for the angle, for the alpha, we got 108 degree. For beta, we get 21.8 degree. For the gamma, we get 77.6 degree. Okay, now we are going to talk about the part 3, which is equilibrium. So I will start by talking about the equilibrium of a particle. Like this is the particle. Although it has force 1, force 2, and force 3 and force 4 added on the particle, but this is in equilibrium. Because the force added on it is in a equilibrium. So when the particle is in equilibrium, is when the particle is at rest or move in a constant velocity. That means that the resultant force or the total force of these 4 forces is equal to 0. And for the springs, we have the formula, which is force equal to Ks. K is the spring constant, and the S is the distance for the spring to move. Like the spring original is like this height, and after is being pulled is become this. So this is the S. Okay. After that is two dimension we can resolve it into X component and Y component. Because this is in equilibrium, so Fx is equal to 0 and Fy is equal to 0 as well. For three dimension, as we mentioned before, because it's in equilibrium, so the sum of all the force is equal to 0. In X component, Y component, and Z component also is equal to 0. Okay, let's look at example 2. We have a 90-pound load at here, and it is supported by two cable, which is the cable AD here and the cable AC here. And you also stretch the spring for equilibrium, which is AB. So we need to find the magnitude, the force for AD, AC, and we also need to find the spring constant, and not spring constant, the distance for the spring. Okay, first of all, we need to draw the free body diagram. This is very important. We need to keep it in mind. When we solve the question, the first thing first we need to do is the free body diagram, because it helps us to understand more about the questions. So here I already do the free body diagram for the questions. So we need to resolve the force into X, Y, and Z component. Okay, so we already resolved it. And why? This is we already get it just now. Like Fx is equal to 0, Fy is equal to 0, and Fz is equal to 0. Because as the question mentioned just now, this system is in equilibrium. After that, we can solve this equation to get the Fc, and we can solve for this equation for Fd. Because we get the Fc, we just substitute the Fc at here, and we can get the Fd at here. And last but not least, we can get the Fb as well. So now we can get calculate the stretch of the spring. As I mentioned just now, the formula for spring is force equal to Ks. So this is the unknown we want to calculate at here. So the F is this one, we just substitute, and the K, we already get it. The question already give us just now. So this is what we want to find. So here is the answers. Okay, now we are gonna to talk about the equilibrium of a rigid body. So for a rigid body in rest, or translate with a constant velocity, the resultant force is equal to 0. And here's the new thing, which is couple moment. Before this, we just look at the resultant force. And now we have the couple moment as well. So for resultant moment and couple moment, both are equal to 0. For two dimension, it's very important, as I mentioned just now, we need to draw the free body diagram. And what we need to have include in the free body diagram. First, we need to have the couple moment. The couple moment is this one, which is this one, the blue arrow here. And the next thing is we need the force, which is this one, force FBC, and we need the angle as well, which is here, 30 degree. And we also need the dimension, which is 2 meter, 1 meter here. Yeah. Why we need the angle? Because we need the angle to resolve the component into X component and Y component. And here are some common type of support, which is roller, smooth pin, or hinge, and fixed support. And for this support, they will exert force and couple moment. So we need to take an account for the support. So the most direct solution for us to solve it, which is we sum all the forces along an axis. Like for example, in this situation, in this example, we can sum the Fx equal to 0, which is, we can see for the X component, we have Ax and the P2 here. Because they acted in the opposite direction, so Ax is minus P2, which is equal to 0. After that, we also can sum the moment about the point A equal to 0. So yeah, here is the formula that we can get. And now is about the 3-dimension. Here also some common support for 3-dimension, which are roller, ball and socket, and fixed support. Like it is more advantageous for us to use the Cartesian vector to analyze the 3-dimension. So this is the common equation of equilibrium that we apply for 3-dimension, which is the total force is equal to 0 and couple moment is equal to 0 and x, y, z component also equal to 0 and the couple moment, the x, y, z for couple moment also equal to 0. And now we look at the determinacy and stability. For statically determinate, which is a body supported by a minimum number of constraints, which is also means like support to ensure the equilibrium. And this is the proper constraint. And for statically indeterminate, it has more support than required to ensure the equilibrium. How we can determine the statically determinate and statically indeterminate? For statically indeterminate, we have the unknown more than the equilibrium equation. Like for this example, the unknown we have MA here, AX, AY, BY, and CY. We have 5 unknown in total, but we just have 3 equilibrium equation, which is Fx equal to 0, Fy equal to 0, and couple moment equal to 0. So from this, for this situation, we can determine it is statically indeterminate. Like, let's look at the example 3 for root AB here. It have a 200 Newton force. So we need to determine the tension of the BD, which is here, and the BE. Okay, first thing first, as what I mentioned before, the most important thing is free body diagram. Yeah, here is the free body diagram for this question. So as I mentioned just now, to solve the 3D Cartesian, 3D vector like this, it's more easy for us to represent it in Cartesian vector. So we can represent it in IJK, which is the Cartesian vector. After that, we can apply the force equation, which I mentioned just now is Fy equal to 0, total F equal to 0, all those things. We can apply it here. So we can get this. So we also summing the moment, couple moment about the point A at here. So finally we can get here. So after that, we can solve all the equation that we get just now, and we can get the tension at D is 100 Newton, tension at E is 50 Newton, and we can get all this. Okay, now is the last part of the presentation, which is analysis of friction in bodies and structures under static condition. Like, okay, what is dry friction? Friction, the frictional force exists between 2 rough surface of contact. Like for example, we want to move an object in a surface because it's rough, so it will exist a friction at there. And there are 2 categories of friction, which is static frictional force and kinetic frictional force. For static frictional force, which means that the object didn't move, like the object just stay on the surface. So we have the formula, which is Fs equal to micro s Newton. This the micro s here is coefficient of static friction. So here's the second one, which is the kinetic frictional force. when the kinetic frictional force occur, which is when the motion occur, like this is the surface, and here's the object when the object move like this. So here is the unit for us to solve for the kinetic frictional force. Okay, so when we solve for the problem, we have some unknown we cannot be determined. So in this case, we need to consider for the shredder objects, or also the slipping also occurs. So we need to take in account for this one. So here's the wedges. The wedges is the inclined plane. As we can see here, the inclined plane to increase the application of force. So the Fs is equal to 0, Fy also equal to 0. And when the coefficient of friction in the wedges is large enough, which means the coefficient of friction between the surface is large enough, which means the force, the driving force here, we can be removed, which means that wedges is in the self-locking condition, which means it will remain in place. Here is and the next one is the screw. Screw is a square-threaded screws. Square-threaded screws is used to move the heavy load. So the moment of the screw depends on the coefficient of friction and also the angle. And the coefficient of friction between the surface is large enough, the screw also in the condition, which means the self-locking conditions. So here are the formula for us to solve the screw-related problem. So for the phi here, which means is the angle of static friction. Another thing is flat belt. Flat belts, this is the flat belt. So the force need to move the flat belt it depends on the angle, which is this one, beta, and also the coefficient of friction. So here is the formula for us to solve the flat belt related question. And the beta here is the total angle of belt to surface contact. And bear in mind the angle for the beta need to be in radian, not in degree. And this one is the coefficient of friction. And here is the collar bearings and this. For normal force, the normal force for this one is determined from the force equilibrium along the shaft. And the moment, this one, the moment to turn the shaft is determined by the moment equilibrium. So here is the formula for the collar bearing and this. Here comes the journal bearing. So here is the formula for it, and M is stand for moment, which is this one, moment, and I is bearing reactive forces, and R is radius, which is from the center of the bearing to here, which is the radius. Yeah. So and the phi here is the angle of kinetic friction. And here is the rolling resistance. So the resistance of a wheel to rolling over a surface is caused by localized deformation of the two materials in contact. So here is the formula for rolling resistance, which is P equals to WA divided by R. P is stand for driving force, W is stand for weight, A is coefficient of rolling resistance, and R is the radius. Okay, so here comes our example 4. So it is observed that the bed of the dump truck is raised to an angle of 25 degrees, which is here. So the vending machine will begin to slide off the bed. So determine the static coefficient of friction between the vending machine and the surface of truck bed. Okay. here comes our free body diagram, which is the most important thing before we need to do our questions. We need to analyze our question first by doing the free body diagram. Okay, so the X, as we can see, the X here is used to localize the position of the resultant normal force N here. So the equation of equilibrium, we have Fx equal to 0, Fy equal to 0. So we need to write all the forces added on X component at here and Y component at here. And here is the couple of moment also equal to 0. So since the slipping in bed at the 25 degree, so we can use the equation 1 and equation 2 at here. This one, as we mentioned just now, the unit about the formula we mentioned just now, then we can use it, and this we can get the static coefficient of friction is 0.466. Yeah, so here comes the end of my presentation. Before I end my presentation, let's recap or review what have I present just now. At first, I have talked about the basic concept of static. And in the basic concept, I have talked about the basic quantities and idealization and also the Newton 3 laws. At the second part, I have talked about the force system. For force system, I have talked about the scalar and vector, 2D force system, and also 3D force system. For equilibrium, I have talked about the particle equilibrium and rigid body equilibrium. Last but not least, I also have talked about the analysis of friction. All right, that's all from my presentation, and thank you for watching.